fifth mini course of the ALGA by Susanna Zimmerman, and she will tell us about quotients of groups of birational maps. Please, Susanna.
Yeah, thanks a lot for the invitation. So, yeah, I'm pretty excited to be here. Well, as the title says, the aim of the course is to give you one way to construct. So we consider birational maps, group of birational maps. These are abstract groups, and we want to study these groups. I want to know properties of these groups. And one property that I want to know is, can I produce smaller groups? Okay. So the aim of the course is to motivate you a way to obtain group homomorphisms from these groups. Okay, and we do this using birational geometry. So I'm not entirely in group geometry. Okay, so throughout the course, a surface will be smooth and projective, and a priori will work over perfect fields. Okay. I will get to it in a bit. So let's say, okay, so for me, a surface is projective. But it might happen that sometimes I give examples of birational maps and I will give them in local coordinates. Okay, but you just imagine that they extend to the compactification. Okay, and then so a priori or some field. Okay. Okay, so so there's a bunch of things that I wanted to introduce that Cinzia has already introduced. So thank you, Cinzia. And now I'm not quite sure exactly how to introduce my things anymore because, yeah, okay, it changes a bit of what I prepared. So just to recall you, a birational map F from X to Y, so between surfaces. Is an isomorphism between dense open sets. Yeah. And well, my surfaces are integral. Okay. So dense just means non-empty. Okay, because dense open sets always intersect. This is like a well-defined equivalence class. Okay, so some examples. The prime example is, well, isomorphisms. But then the easiest one that we see that is not an isomorphism is a map from P2 to P2. And we send x, y, z to 1 over x, 1 over y, 1 over z. It's an involution, okay? And it's defined whenever a priori x, y, and z are non-zero. And this is the same as x, the map given by yz, xz, and xy. It's an isomorphism from the open sets where x, y, z are non-zero to itself. And so if x and y are smooth, F is always defined or outside a finite number of points. Okay, and it is an isomorphism outside a finite number of curves. So we can see this for this example, or examples of bilateral maps from P2 to P2 in general. So we have a bilateral map is given by coordinates that are homogeneous polynomials in x, y, and z. They have to be of the same degree so that the map is, so that this makes sense. And let's say they have no common divisors except scalars. And then, well, this is this map is defined. This is not defined exactly when f0, f1, and f2 are 0, and this is a finite number of points. And where is it an isomorphism? It is an isomorphism wherever the derivative of this map is invertible. So we compute the derivative. This is still f. I'm going to say xj, even though I put xyz, but it's x0, x1, xz. Okay. And it's invertible when the determinant is non-zero. So this is and when the determinant is 0, that means the derivative is not an isomorphism. So that means it contracts some subspace of some tangent space of the tangent bundle. And that means it contracts a bunch of curves. So in this case, for this example, let's say this is f. We have, so I'm going to see it, we have 0 on the diagonal. Then we have z, y, we have z, x, and then here we have y and x. And this is a multiple. If you compute the determinant, you get something like, I think, 3xyz, or minus 3 or something. So this is exactly, this gives, the 0 of this is exactly the curves contracted by this map. And it contracts these curves exactly onto the points on which the inverse is not defined. Okay, so maybe for here, we have P2, we have the 3 lines. And then we contract x equal to 0 onto (1, 0, 0). So this map, this line here is contracted into this point, and y equal to 0 is contracted. Ooh, I'm sorry. I'm going to change my page. Okay. So the red line onto the red point, the fat line onto the fat point, and I have the yellow line onto the yellow point. So basically, a birational map is an isomorphism on dense open sets. And outside a maximal dense open set, it contracts curves, and it takes points and makes curves out of it. Okay, maybe another example. So I'll give you the map in local coordinates from A2 to A2, and I'm mapping xy to x, and then axy plus bx, cxy plus dx, and abc and d are polynomials, or a priori rational functions in x, and ad minus b, c is not 0. So then, do you see that this is a map preserving a fibration? And depending on the point, it acts like a Möbius transformation on the second coordinate. And what it contracts is exactly the determinant of this matrix. Okay. And then maybe another map. I'm sending xy to x plus p of y, for some polynomial in y. And the inverse of this map is just a minus here. That's actually an automorphism of A2. So on A2, nothing is contracted, no indeterminacy points, but it does contract something at infinity. It contracts a line at infinity. Also here, something at infinity may be contracted. Well, if the degree of P is at least 2. If the degree of P is 1, this extends to an automorphism of P2. Okay, and then, so your X is the group of birational maps. Of X. And this is an abstract group. It can happen that this is, for certain varieties, this is a finite group. It can even be an algebraic group. But I will consider it in the case that I'm interested in. It is none of those. It's infinite. It's not of finite dimension. And one can even show that it doesn't have a reasonable algebraic structure on it. So this, for me, is just an abstract group. Nothing more in it a priori. Okay, and we're interested in it when X over the algebraic closure is rational. So this is X extended to the algebraic, the same variety but seen over the algebraic closure. And the aim is to find a homomorphism of groups from Beer X to some interesting group. Now, a priori, we remember a bit of group theory. It's easy to find other, like these homomorphisms. You just put G equal to Beer X, you put the identity, done. Or you put the conjugation by an element of Beer X, done. You have a group homomorphism, but I want something smaller. So I want to have a finite group here. Okay, so why is this a course and not just I'll give you the homomorphism and we are done with it? It's not so easy to find these homomorphisms a priori. And one of the reasons is the following. So, the basis is a very old, very old theorem that dates from the Italian school who was studying Cremona groups. And that gives a generating set of the group of rational maps when X is rational. So if K is algebraically closed, then the group of rational maps of P2 is generated by the automorphism groups of P2 and the map, the quadratic map we saw earlier. And so I discovered last November, I think, what was the motivation for this theorem. I didn't know until then. So, like more than a century ago, people were about to classify curves, and they took curves and they desingularized, and desingularizations are done for curves are done with blow-ups of points, so sigma transformations. And I think at some point people were wondering whether, like they were noticing that they just used basically versions of this map, and they were wondering whether they could do better, or this was all they got. And so Noether came up with this theorem, and he gave a proof that had a hole in it, and then Castelnuovo filled the hole. So basically the motivation of this theorem comes from classification of curves, I think. Okay, so what about it? Okay, and then a corollary of it. So there is K is algebraically closed. Then there is no non-trivial homomorphism of groups from the Cremona group to a finite group. So the proof of this is relatively straightforward if you have the theorem. So first of all, K is closed, so right. So the automorphism group of P2, this is PGL3 of K. Okay, so suppose there is some group homomorphism from your P2 to a finite group. Then, since K is infinite, this group is infinite. So there is a non-trivial element of PGL3 that is mapped onto 0. Or to 1. Well, the trivial element of G, anyway. Okay, so, but K is algebraically closed, so PGL3 is also PSL3. And PSL3 has no non-trivial homomorphisms. So it has none, it's a simple group. This is PSL3, okay. Has no normal subgroups. And what this means is just that phi of PGL3, the automorphism group of P2, is sent onto 1. So the smallest, I mean, so here, maybe if you don't remember, so the kernel is a normal subgroup of BRP2. So it contains the smallest normal subgroup containing alpha. But the smallest normal subgroup containing alpha also contains PSL3 because this one does not have any non-trivial normal subgroups. Okay, so. Okay. Right, so maybe even more, it contains the smallest normal subgroup containing the automorphism group. So now we write H to be the automorphism of P2 given by -1, 1, -1, 1, 1. And if I pick the minus correctly, this is an involution. And then I have my map, let's say sigma. And we have sigma H to the power of 3. This is the identity. You can compute it straight away. And then with this, what you get is that sigma is H sigma H, right? Yes. So H and sigma are involutions. Actually, here we have this. Okay, so this is sigma H, H sigma. So this is a conjugate of an automorphism. And as something conjugate to an automorphism, it's contained in the smallest normal subgroup containing ODP2. So all the generators of BRP2 are contained in the kernel. Of our automorphism. So this means that if we want to find homomorphisms from the Cremona group to finite groups, algebraically closed fields are not the ones we work over. So we'll switch to other fields. Now, there are two types of fields that are now closed that you can work over. And the first type are perfect fields. And the other type are imperfect fields. And perfect fields, this means that every irreducible polynomial over that field has distinct roots, has only distinct roots. So and then imperfect fields are the other ones. So here, for perfect fields, any field of characteristic 0 has this property. And then finite fields have these properties. And then fields which are imperfect are, for instance, function fields over finite fields. Why? Because we can look at x to the power of p minus t. This is irreducible over this field. But over the algebraic closure, we can write it x minus square, the 1 over p times p. And then this has only one root, p multiple root, p tuple root. So it has one root. But it's of degree p. And so the construction I want to show you works over any field, but I'm going to stick to perfect fields because I find the geometry a lot more intuitive than the one over imperfect fields. Okay, so we're going to stick to these. Also, most of what I'm going to tell you over perfect fields will not depend on the characteristic of our field. Whereas if we work over imperfect fields, some things work over some characteristics and some things don't. So here we don't have to worry so much about the characteristic. But just to mention, so maybe in general contexts, if you're not particularly interested in non-closed fields on surfaces, they come up very naturally in general if you're interested in birational geometry on higher dimensional varieties because of the following. Let's say, depending on your interests, if you have a fibration, let's say a contraction of fiber type, then the generic fiber X is a variety of over K of Y. Okay? And then this field falls into one of these two categories. It will not be closed in general. And then if you're in characteristic 0 or over finite fields, you will stay over perfect fields. That's fun. If you're working over finite fields in the first place, you will get to work with imperfect fields, and then you're a bit in more trouble. So this is not closed. And the idea would be that So if you do know this variety over this field, then you may be able to extract some rational geometry of this vibration. Okay. I forgot what time is it. I think I didn't. Oh, okay. All right. Okay. Great. Okay. So let me explain my point of view over perfect fields. So basically, the point of view is that, okay, of course, you can work just on surfaces over non-closed fields directly, but with perfect fields, you can equivalently work like over closed fields, but with a group action. And then you can do anything you want that you know of. It just needs to be equivariant with respect to your group action. And the base of this is that if X is quasi-projective, and then we have a bijection between, well, we have a bijection as quasi-projective setting. Let's see. Let's do this. Then we have a bijection between varieties over K. K is perfect. And varieties over the algebraic closure, so plus the action of the Galois group, of the total Galois group, such that all orbits are finite. So orbits of points are finite, orbits of curves are finite, orbits of subvarieties are finite. And the bijection goes as follows. So we have X, and we just extend to xk bar. So that's X extended xk bar. And then on spec k bar, we have a group of the action of the Galois group. And then in the other direction, we have some variety y over k bar plus an action of the Galois group, and we just quotient out by the action of the Galois group. And this is where the fact that the action all orbits needs to be finite comes in. So this is due to Borel and Serre. And so here you have varieties over K, and these are called K forms. Okay, so let's go with an example. We have on one side P2C, and then the Galois action, so we have K equal R. Okay, the Galois group of C over R is just the complex conjugation. And we can act by complex conjugation on each of the coordinates. And on the other side, we have P2 R, which is just P2C mod this action. So then, for instance, on the right-hand side, we have complex conjugate points, pairs of it. And on the left-hand side, we have a point of degree 2. So here, that's 2 points. They are exchanged by the Galois group. And here we have, well, a point of degree 2. Or, well, here we have a conic that is a singular conic that is integral over R. And here we have 2 lines that are exchanged by the Galois group. Or we have a conic without any real points. So this equation has no real solutions in P2. And here we have, on this side, we have P1C with the action, I think it's minus U. It's 1 over, which one do we have to take? I will go like this. Here we have, oh, it's, yeah. That's this one. Okay, another example. Maybe, okay, this is Q of square root of 2. We have here, we have x squared plus 2y squared equal to wz in P3 over K. And then this is a form of P1 over Q bar times P1 over Q bar, and I'm sending not Q1. I'm gonna stay with R, otherwise I will get confused, I think. To V naught bar, U1 bar, U naught, U1. So I'm saying over C, I can resolve this, this equation. I will get a P1 cross P1. Sorry, then I need to put C here. And this isomorphism will induce you this type of complex conjugation on P1 cross P1. So what happens if our field is not perfect? So I cannot see geometrically really anymore what is happening. I don't have a group action. So if K is not perfect, I don't have access to the total Galois group. And then, for instance, if my K is F2 of T, I can look at the conic y squared plus t x squared equal to 0 in P2 of K. That's an integral conic, but over the algebraic closure, it is a double line. So I don't see two lines that I can exchange anymore. I just see a very fat line. Okay, so this tells you, this bijection tells you that if you work over perfect fields, you can do anything you want that you know how to do over algebraically closed fields, as long as you do it equivariantly with respect to the Galois group. Okay, so then I wanted to put is that this case perfect and x, so x a quasi-projective variety, x in existing point, and x over k bar becomes a union of, a union of both points over k bar, and n is exactly the degree of the function field of x over k. Okay, so we look at, well, we can look at the projection to a point, okay, to a rational point. Then this induces an injection of k into the function field of x. Okay, that is finite of degree k of x over k. Okay. And that corresponds exactly to the projection over k bar going from x1 to xn to a rational point, which is finite of degree n. Okay. And then we can say this is the degree of x. So if we had maybe the point z equal to x squared plus 2y squared equal to 0 in P2 of Q, then this is x. Then k of x is q of the square root of 2, because I can make this not irreducible over q of square root of 2, and over this field. So for which this x becomes the 2 points. I have a square root of 2, 1, 0, and minus square root of 2, 1, 0. Now, a consequence for us, consequence of the bijection of between varieties over K and K forms is that Rational maps, we have a one-to-one, we have a bijection between Barational maps. From X to Y over a field and Barational maps from K bar to Y bar that are Galois equivariant. So, like, maybe as an example, that just is for computational. So, an element in the Cremona group over C is defined over R if and only if there is some representation of F with coordinates that have coefficients in R. Okay, and you get, well, you also get an inclusion of beer X into beer X bar. And this is exactly beer X K bar that is invariant under the Galois action. Do you have any questions so far? Now, we might be, so we've already seen for P2, for rational surfaces, we cannot get a homomorphism of groups to a finite group from this group, but maybe from this one. So we'll have one from this one, but it doesn't extend. And the reason is already what I told you. So maybe, because it's possible that there are elements here that are not conjugate, but they're conjugate here. Okay, and so maybe, yeah, or maybe for this, an example. So it's not a very complete example. It's just something to motivate what I just said. So we have, so let's consider the involution from P2 to P2 given by xz, yz, and x squared plus y squared. So this is just in affine coordinates. This is the involution at the circle. In my thesis, somebody told me this is the oldest involution. It's a Greek involution, the involution at the circle. Okay, so it contracts what? It contracts z equal to 0, so 3 lines, z equal to 0, and then x plus iy equal to 0, and x minus iy equal to 0. Okay, and it is not defined. 0, 0, 1 at this point, and then 1 I 0 and 1 minus I 0. So over R, it contracts a rational curve and an irrational curve. Right? This is an integral conic over R. So this this map, what was it? Maybe tau. So tau is not a composition of the standard quadratic involution and automorphisms. Because the standard quadratic involution, we saw that it contracts 3 lines, so rational curves. And then any composition of automorphisms on this map will only contract rational curves. But this one contracts an irrational curve. So it cannot appear as a product of these elements in these. Okay, so this tells you that the Noether-Castagnolo theorem we saw earlier fails over R at least. Okay, so So a priori, we have a chance of maybe constructing a homomorphism because the lemma we saw earlier does not work. Oh. Yes. Well, because so there is, we do know a nice generating set, but you add this to the generators, this map, because you cannot get it from these. Because, so this one only contracts 3 rational curves. So if I take Cremona, automorphism, Cremona, automorphism, Cremona, automorphism, this composition will only still contract rational curves.
But Cremona also extracts points.
Yes, but on 2 rational curves. So maybe that's an important thing. If you have an indeterminacy point that is a rational point, the map makes from it a rational curve. If you have a point of degree 2, the rational map makes out of it a curve that over the algebraic closure is the union of 2 curves. So here, what happens is that I contract these 2 curves. I contract them onto 2 conjugate points, and these rational curves I contract it onto a rational point. So if I can only contract rational maps, I only ever get rational base points. My iPad has given up. I cannot charge it, so I'm going to have to freestyle it from here. All right, so this is not just for R. It's a nice example over R, but we can go further. So let's say we have some polynomial in Y that is irreducible and of degree very large. Okay. We look at the map from A2 to A2. I mean, it's from P2 to P2, but I'm giving it in local coordinates. So I send xy onto x p of y, y. Okay, so it contracts the curve p equal to 0, which is integral over k, because we chose p to be reducible. Sends it onto the point y and p equal to 0. This is a finite number of points. Actually, since if we assume that our field is perfect, it contracts it exactly onto how many points? The degree of p. So this is t points that are permuted over k bar, permuted by the Galois group. Okay. So now, again, with the same argument, this map contracts only rational curves. It has only rational base points. If I have compositions of automorphisms and this map, I will only ever contract rational curves, and I only will ever get rational base points. So this map cannot be contained in a group generated by these either. So and in fact, if the degree of k bar over k is not finite, then this means that I cannot generate the Cremona group by these, and adding like a finite number of these. Okay. So it means that I cannot generate the Cremona group by a set of bounded degree. Bounded degree means that the degree of the coefficients is bounded universally. Because I can always take some, so let's say I take a bounded set, I look at the group generated by it. The bounded set has coefficients given by this bounded degree. Then I can just take a polynomial of higher degree that is irreducible, and then this map will not be in that group. Okay. So you can see that like the more complicated the field, the more complicated the group becomes. And the idea is that the more chance we have to get some interesting group homomorphism from it. And so how to construct group homomorphism. So we go back a few years to bachelor, and we remember that when we had a class on groups, we had a group, maybe it was finite, maybe not, but we had a set of generators, we had a set of relations. You send your generators somewhere, you check that the relations are sent to 1, and then this gives you a group homomorphism. Okay, so you have a group, some generators, you have some relations. You send them to someone. This is in H, and you check that the relations are sent to 0. So for this, you need to have a generating set, and so for the groups we want, for instance, for the Cremona group, for BRP2 over algebraic closure, over an algebraically closed field, we already saw from the set of generators that we were never going to get something interesting. So what is over fields, over other fields? I cannot make it. So we do know generating sets of the Cremona group over other fields. So for k equal So for k equal to r, there is a very nice generating set by Blanc and Mangot from 2014. And it is bounded of degree 5. Okay, the generators are the automorphisms of P2, the two quadratic maps we've seen so far, and then a family of transformations of degree 5 that I will not introduce. And then in general, for perfect fields, we have one by Iskovsky, Kaptikairov, and Trigup. I'm sorry. And I think, I'm not sure I remember, but it's from the end of 90s, I think. And the list of generators is like 5 pages long. So, we have generators, they even have relations. The set of relations is even more pages, and, well, we don't want to work with it. So this puts a sort of break in our idea, but then these sets are just so big because they insist, their creators insist of staying inside the group. So we apply a very, very old trick, and we take our group of interest. We take our group of interest, and we put it in a bigger group. Where we know generators and relations that are nice. And then we construct a group homomorphism here. And we hope that the restriction is not trivial. So this way we can completely avoid generating sets of a group that are too big. How much time do I have? 25 minutes. Okay, so who is this group? So, in maybe a bit too simple, but not incorrect, or maybe just non-precise. So G is just a groupoid of birational maps. between minimal models. That are rational, minimal models. We can replace P2 by some surface we like, and then instead of rational, we have birational to the surface we like. Okay. So this means, so basically, instead of looking at birational transformations from P2 to P2, we allow other surfaces that are not P2, as long as they are minimal in some sense. But this means that the birational maps we look at, their domain and their target are maybe not the same, so this is not a group anymore. But we can invert birational maps. So this is the type of group we're looking at. And then what we're going to construct is homomorphism from a groupoid to a group. A group is also a groupoid because you can invert. And then the restriction of a homomorphism of groupoids to a group, from a groupoid to a group. If you look at the restriction to a subgroupoid that is a group, it becomes a group homomorphism. Okay, that's okay. So here we will not have a group, we'll have a groupoid, but here we'll have a group, and here we have a group, and this will be a group homomorphism. Okay, so this is a groupoid homomorphism. Here we have a group, and this is a group homomorphism. Okay, so let me talk about the minimal models. So here, thank you, Cinzia, for your course, because many things that I wanted to say, you've already kind of said, only that since we're working on surfaces, they're a lot easier. Because when we contract, our birational contractions are just contractions of a bunch of -1 curves that are permuted by the Galois group. So, okay, so. So maybe blow-ups over or perfect fields. We can always blow up rational points the way we always have over algebraically closed fields. Okay, so we have so we have the blow-up of 1, 0, 0. Okay, as always. And then from here, if we want to blow up blow up, let's say, a point of degree 2. So for us, this is 1 I0 and then 1 minus I0 that are exchanged by the Galois group. Then we just blow up each individually, and then, so we blow up P2 in 1 I0, and then 1 minus I0. And so here we have an action, the action of the Galois group of C over R. And if we just blow up one of these 2 points, the action doesn't live because we lived only one in the orbit. But if we blow up both, then the action lifts to the blow up. Okay, so general. Okay, so if so we have a surface, a smooth point in the surface, then the blow-up of x in that point. This corresponds to the blow-up of, let's say, we have x over k bar. That's a bunch of points. And remember, because our field is perfect, I didn't say it, but this is important. So because our field is perfect, all of these are closed points. They're reduced points. Okay, so these are all reduced. Closed over k bar. So we can blow up just a set of these. And we have the Galois group lifting. Galois group acts on x k bar, and it lifts, the action lifts onto the blow-up of all these points. And this is a k form of this. So if I extend this variety over k bar, I will get this. Okay, and so I have a point here. I will get some exceptional divisor. And then here on this side, I have a bunch of points that are permuted by the Galois group. And when I blow up, I get a bunch of -1 curves that are permuted by the Galois group exactly the same way that it permuted the points. So this means when we apply the MMP over an algebraically closed field, we just look for -1 curves, and we contract the -1 curves we find. And over a perfect field, we find -1 curves, and then we have to look at the orbit of this -1 curve. And if every member of the orbit, if they're all pairwise disjoint, we can all contract them together. And then this is the MMP we are looking for. So over k bar, we find a -1 curve and contract to a smooth point. So some perfect field, we find a -1 curve over k bar such that its Galois orbit consists of pairwise disjoint curves. Every curve, so the Galois action preserves self-intersections, so every curve in this orbit will be also a -1 curve. If they are pairwise disjoint, we can contract them. And then the Galois action descends. And we contract our orbit onto an orbit of points that over k will give us a closed point. So here, every time we contract a -1 curve, the picarang drops by 1. And here, every time we contract an orbit, the picarang drops by 1. So count of picar number is So for us, maybe the picker number is the, let's keep the notation. I want to down. So I had this, I had a dimension of the space of 1 cycles. This is over an algebraically closed field, and this is over a field. And here, I will just take n1 of x k bar, but then I will have the part that is Galois invariant. Okay, so maybe, yes, go for it. So there's always the canonical divisor, which is invariant. So this is okay. Yeah, yeah, thanks. So at least one. Maybe I'll make an example. How much time do I have again? All right, okay, okay. So just, this is an example not of the blob, but just in terms of picker rank. So in blob, in P2, 2 points that are Galois conjugate. So a point of degree 2. This is x1, x2. And then a priori, so the Néron-Severi group is of over C. This is my x. Over C, this is set of a line plus the exceptional divisor of x1 plus the exceptional divisor of x2. But over R, these two are Galois conjugate. And then also their exceptional divisors are Galois conjugate. So that means E1 and E2 are not defined over R, but their sum is. And then the Néron-Severi group of X is actually the pullback of a line plus the curve, the union of these two. So the blob of a closed point makes the picker number increase by +1. Okay. So if I take this orbit and I contract it, even though over the algebraic closure I can contract 2 curves, over my field, this counts as 1 curve because I need to consider the orbit of the Galois group, and then I can contract 1 curve and then the picker number drops by 1. Okay, so that means this, just the way we know that, so every time we contract the -1 curve, the picker number drops. This way we know that our MMP finishes at some point. And in the same way, the Galois equivariant MMP finishes at some point, because every time we contract a Galois orbit of disjoint curves, the Picard number drops by 1. Okay, so at some point this finishes. So. Do you have any questions on the equivariant MMP? So maybe just a side information, you can do an equivariant minimum model program whenever you have a group action that is reasonable with respect to orbits. It can be a Galois group, it can be an algebraic group, it can be some weird abstract group, as long as it preserves the intersection numbers and its orbits are finite. That's more or less what you need. So another way to see it is that you have your Galois group acts on the set of curves. It preserves intersection numbers, so it acts on n1 of x on your 1 cycles, and it preserves the NE, the cone of names, NE of x. There's no names, right? So, okay, maybe the more abstract way to see it. So you have Galois acts on the space of 1 cycles. It preserves intersection number. So it acts. And it preserves the canonical divisor. So it acts on an E of our variety. And it permutes extremal arrays. Okay. So you can, even abstractly, you can the MMP, you can make it equivariant by just contracting extremal arrays in the same orbit, as long as the corresponding curves are disjoint. Okay? So why I'm just insisting of disjoint, because if I have 2 - 1 curves and I contract one, this one becomes a 0 curve and I cannot contract it any further. So this is why it's important that our curves are disjoint. And so the same way, you can make the MMP equivariant with any random group you want, as long as the action on NE is reasonable. Okay. So this way you can just take any finite group, algebraic groups. Okay. So now. Okay, equivariant MMP terminates. And classically, what does it terminate in? Sort of the same thing as our algebraic closed field. So either your K is naive, the canonical is naive, the anti-canonical is ample, or there exists some conic bundle over a curve. In the same conic bundle, in the same definition that Cinzia gave earlier. So every fiber is a plane conic, and the general fiber is a P1 over some field. Okay. let's say maybe, okay, generic fiber is a plane conic plus all fibers are one-dimensional. Yes, I think this is good. So I will write down an example to tell you why I'm having I cannot just copy-paste the definition of Cinzia. So I can look at the following I have to think about what example I want to put. No, so it's basically a conic bundle. We have we allow some singular fibers that are two lines intersecting. So this is the image, the picture of the algebraic closure. But then maybe some fibers are above points that geometrically are Galois orbits, and then these fibers are Galois orbits. So is a P1, but over the function field of the point. Okay. So, all fibers are P1s. All fibers over the function field. Of the corresponding point. Okay. I see some knots, I see some non-knots. Okay, and what we're going to be interested in is those two. Right, I forgot. Okay, so we have conic bundle, and we have so the Galois invariant Picard rank, Picard number is 1. The Galois invariant is 1, and here the relative Picard number is 1. Yeah, and these are called the Bethe surfaces. Okay, so maybe to give a full circle ending. So these two here, they're called Mori fiber spaces. These are the Mori fiber spaces in dimension 2. And so what we do is we take here X. Maybe we started with X. We start from X. We embed it in the groupoid, so in the groupoid of birational maps between Mori fiber spaces birational to X. And we construct homomorphisms here, a lot of them. And then we will restrict to Z and check whether this is non-trivial or not. Okay. So what I want to do in the next lecture is to give you a generating set and a set of relations of this groupoid. And then I will give you the construction, okay, of these. This is a construction by Julia Schneider from, I think, 2019. And in the last lecture, I want to give you the analog in higher dimension. I will not go into details into higher dimension, but I will give you a sort of quick overview of how to generalize all this in higher dimension. Okay, that's all I wanted to say today.